Okay, so this is. Do you remember when we talked about areas of regions, and we actually started by just defining regions. Like what set of points is that? So here's a little extra credit task. I'll give you some key points here. Show up. Yeah. Okay, and then symmetric on the other side. So I have created this image with one line in GC and no commas. One line with no commas. Okay, so in the spirit of defining a region as a set of points, right? Defining a region as a set of points. This was you can do this with one line, one GC command, no commas. You can define this set of points. One line, no commas. Not piecewise. Okay, so it's a challenge. That's why it's extra credit. So if you want to attempt that, and then along with your line, explanation of why it works. So I know that you understand it and didn't happen to get it from someone else. Okay, explanation of why it works. So the joy is in figuring it out yourself, like working at it, making progress, working at it, and getting it in the end. Okay. I don't know, a week. Let's say Wednesday. Yeah, Monday. Something like that. Okay. Any questions? Any questions on that? Okay, so we're talking about work. So all that's on the video. If you didn't get that all copied down, it will be on the video. All right, so let's just do a little review and preliminaries before we move on. So work is something applied over a something and is calculated by. So this is the basics now. What work is? Force applied over a distance, right? And is calculated by force times distance, right? So the more force you apply, the more work you'll be doing. The further you go, the more work you'll be doing, right? So force times distance. Force is directly proportional to force and directly proportional to distance. Sorry, work. Work is directly proportional to force. Work is directly proportional to distance. Okay, so then what about our net accumulation of work function? So just in the most general sense, what will the form of a function that's a net accumulation of work look like? Let's see here. Kellen, what do you think? Okay. No. See if you can do it from your head. Right. Right. So it's going to be the integral from a to x of whatever the rate of change of work is, right? So this is the same thing over and over again, right? This is the same thing over and over again. If we want to create an accumulation function for some quantity, we know it's going to be Are we accumulating the rate? Are we accumulating the rate of change? This is a key point that we've been, no, Bryce, what are we accumulating? Yeah, we're accumulating little bits of work. And to get each little bit of work, we use the rate of change of work, right? So again, you're never accumulating the rate function. So that's a common thing that students will say. We're not accumulating the rate function. We're accumulating bits of work to get the total net change in work, okay? And each one of those little bits, we're going to use the rate function to calculate each little bit of work. Okay? So, if work is force times distance, and a little bit of work is the rate of change of work times a little bit of distance, what then is the rate of change of work? This is something we didn't really emphasize last time. But if this is a little bit of work right here, right? This is a little bit of work, and work is force times distance, and this little bit of work is rate of change of work times a little bit of distance, then what's the rate of change of work? You should be seeing that it's force. Do you see that? It's force, right? Because this little bit of work is basically force times a little bit of distance. So let's talk about that from last time. So the pushy ant. Remember, this was that first work function that we got. When the force pushing the ant, the force the ant was pushing with was constant, 0.03. Okay, so based on what we're saying, then this is the rate of change of work, right? So we're saying that is force. How is that force? This was the constant force the ant was pushing with. So how is this then the force function? What's going on there? What's that? No, it's not a changing. Yeah, so right. So it's not the force that the ant is pushing with is changing, because that's 0.03. So why is the force changing? If the amount of force that the ant is pushing with is staying constant, how is the force changing in that situation? Do you remember? Yeah. Okay, so it has to do with the fact that we're integrating with respect to what? Horizontal position, right? So this is a function of x. We're integrating with respect to horizontal position of the ant. But is the ant pushing horizontally? It's not on your smartphone. Okay. What's that? What? So how is the ant pushing? Do you remember the curve? It was that crazy kind of curve, right? It's like something like that. But we're integrating, we're accumulating force according to a horizontal position. But the ant is pushing in all different directions, right? So what is this thing doing? It's taking that 0.03 and scaling it. So this is like a unitless scaling factor, so that it would be like the equivalent force in the x direction, right? It's taking the force, right? Because this is the arc length. This is the arc length, the ds, right? This is the ds. So it's since we're accumulating with respect to x, it's taking that force and scaling it so that it's actually the force that the ant is pushing in the direction that he's going, which is not always in the horizontal direction. So this is scaling the ant's force for the direction that the ant is going. And so then in the end, we're accumulating in the direction of x, but we're getting the actual work that the ant is doing because the ant is changing directions. Make sense? So it's still force. So this is the force function. It's adjusted for or scaled for the direction the ant is going. Okay, so another way we could write the accumulation of work function then is it's the integral from a to x of the force with respect to x, right? It's the force with respect to x. So f of t dt. Okay, questions about that? Does it make sense? So this then. So that 0.03 that the ant was pushing, and then along with the direction at any given moment, gave us the force with respect to x, so that we could accumulate just horizontally, but get the right work for the ant. Okay, so now something new here. Let's talk about weight. Let's talk about what weight is. So the weight of an object is force. It's the force of gravity. It's the force of gravity on the object. Another way to say that is it's the force required to keep an object from falling, or the force required to lift an object steadily. Okay? So the table, the force that this table is exerting on my laptop to keep it up is the weight of my laptop. Okay? So the force that the table exerts on the laptop is the same as the weight, is a way of calculating the weight of my laptop. All right, what would the SI units or the metric units for weight be then? Newtons, right? Newtons. Not kilograms. What is kilograms? Mass. That's a different thing, right? That's a different thing. They're related, okay? So how are they related? To calculate the weight or the force of an object, weight force, is m times g. So m is the mass in kilograms, and then g is the acceleration of gravity. So in daily life, it's very easy to think of kilograms as weight, but it's not. It's just, kilograms is just how much stuff, right? How much stuff comprises an object. Its weight then is the effect of the force of gravity on that stuff, and then that's force, okay? So G for Earth is, so on Earth, gravity is, G is 9.8 meters per second per second. So make sure you're not mistaking weight and mass. Mass is in kilograms. Weight force is in newtons. Okay? So if you're given kilograms and you need weight, you need to do m times g. If you're given the weight force of an object in newtons, then you don't have to do mg. You have it. You have the weight in newtons. Okay? Questions on that? All right, so that's what we need to look at this next problem. All that stuff. There it is. Okay. So we have, it says a winch, this thing here, lifts a platform from the ground to the top of a building by a thick cable. The cable weighs 151.77 newtons per meter. The platform structure weighs 2815 newtons. The winch must lift the floor of the platform 93 meters for people to step out to the building's top. All right, so we want to define the work function, the accumulated work. I want to adjust this. As h varies from any height we want to do the most general broad thing. Any height say A to X meters above the ground. This is an A. That's an X. Okay, so we know the basics of work. We know the basics of building an accumulation function. All right, and we know a little bit about weight now. So the real challenge in this problem is really conceptualizing the quantities. Okay, and thinking about the relationships between quantities. So before we just like dig in and try to start like writing equations, let's ask, what are the key quantities involved? Okay, so just an example of what a quantity is would be like the width of the platform. That's what I mean by a quantity. The temperature of the air. Okay, the heart rate of someone on the platform. These are what I mean by quantities. Okay, so the three that I gave are all irrelevant in this situation, but examples of what I mean by quantities. Okay, so I'm going to start attendance. I want you to brainstorm with the people around you. List as many quantities as you can that are important in this situation or relevant. Okay? Ready, set, go. Okay, quantities involved. What'd you come up with? Let's see. Rachel, what did you think? What was the quantity you thought was important? What's that? Just one. One or two if you want. The distance pulled up, okay. So the distance moved. The platform. Okay. What else? Yeah. No, right. Yeah, go ahead. Weight of the cable. Yeah, yes, sir. Weight of the platform. So we want to get a list of everything that's going to be important for us. Somebody else? Yeah, Kylan. Like the height of the platform? Yeah. Right there. So I think we want to just kind of think of the platform as the whole thing is just kind of a point at the end of the cable. So it's a valid quantity, but maybe it's not going to really come into play. We just kind of think of this as just a one place in space, kind of a point, like a point. What else? Yeah. Okay. I don't think we know that, but weight of the people, weight of passengers. Okay. Yes, sir. Okay, gravity. What about gravity? You're saying acceleration? Okay. Anything we've not? Yeah, Bryce. Okay, so maybe let's adjust this. The weight of the cable, what? Like per? Are you saying per meter?
Yeah,
Okay. The force. Yeah, so the upward force on on the platform? Okay. What else? There's another hand back here. So that's the same as like the force in the cable. Yeah. Yes, sir. Ma'am, sorry. Distance the cable has moved. I guess I don't know what you mean. So I think maybe what are you saying, like this length right here from here to here? So the current length of cable extended? Anything else? Okay, so now we have to figure out what is really gonna, what are gonna kind of be our focal quantities. And so when we write this work equation or this work function, key is going to be the independent variable, right? The independent variable is going to be key for us. So is one of these or something else going to be the independent variable for our work function? And no one said work done, by the way, right? That's going to be certainly a very key quantity here, right? Right, the work accomplished by the winch. So is one of these or something else going to be our independent variable? What's that? The height. The height of the platform? It's got to be the height of something. So I think we mean the height of the platform, right? When we say the height of the cable, I mean the cable is all of this, right? So we're talking about like the height of like at the bottom of the cable, right? Is that going to be our independent variable? Is that changing? It's not on your smartphone. It's going to be a changing or a constant quantity. Yeah, that's going to be a changing. That's right, because independent variable, right? Variables vary. All right, so we've got our height of that is going to be the independent variable, and then the dependent variable is going to be the weight of the cable. Is our dependent variable? Yeah, it's going to be the work accomplished so far if the height of platform is at its current height, right? So how much work has been accomplished so far to get the platform to that height? That's going to be our dependent. So dependent is work accomplished. And then the independent is going to be the height of the platform. These are both changing quantities, right? So now we need a strategy. How are we going to write the work accomplished, a function for work accomplished or work accumulated for any given height that the platform is at? We need a strategy for that. So we need to think through that. So I'm going to keep taking attendance. Think about what's the strategy. So I'm not asking you to write down the work function now. I'm asking you to think about what's going to be our strategy from if we have the height building up this accomplished work function. So we're looking at the pieces of it, right? And thinking about what pieces do we need and how are we going to get each of those pieces. Okay? Talk about it. Go. Okay. So what do we come up with here? If we're going to try to build the work accomplished as a function of height, what's going to be a strategy? What are we going to need here? So just talking strategy. Okay, so force over the distance traveled. So can you be more specific? So we want work as a function of height.
So we need the force function times the change in height.
So we need the force function. We need a force function. So is the force on the winch constant? No. So yes, let's talk about the force on the winch. That's a really important quantity we didn't mention before. So force on the winch. And so in general, what is the force on the winch? How can we kind of just not write it down completely accurately and specifically, but in general, what's going to be the structure of that, the force on the winch? So we're going to always have the weight of the platform, right? So that's just simply what? 2815, right? But then we're going to have the weight of the cable. And the weight of the cable is constant or varying? Okay, so the weight of the cable, weight is force, right? So the weight of the cable is going to be varying. So we're going to need the weight of the cable, and that's going to be a function of what? Height. So the height of the platform. So we want the weight of the cable as a function of our height of the platform. So we'll need to work on that. And once we have that force of the winch, so we'll have F as a function of H, right? Then what from there? So, and what do we know? What is the force when the platform is at that height? That's the same as what? Talked about that earlier. That's going to be the rate of change of work. And then we'll be home free, right? Then we can write the work accumulation function because of the rate of change of work. So really, our challenge here now is to get the weight of the cable as a function of height. All right, so how are we going to do that? So I'm going to make progress with that. Okay, so then okay, so he's saying, first of all, look at what will the length of the cable be at any given height? 93, the whole minus the height. You see that? So, important quantity, the current length of the cable. The current length of the cable is always 93 minus how much height the platform has. Okay? And so then that's in meters. So if the length of the cable is 93 minus h meters, then what's the weight of the cable? The weight of L meters of cable. What's the weight of L meters of cable then? Samantha. What times L? Remember, this is the weight of the platform. You got the right idea, but you want to multiply by the weight of the platform. What do you want to multiply by? So we have if every meter weighs 151.77 newtons, and we have this many meters of cable, 93 minus h, then the weight of the cable is? Do you see it? Does it make sense? So at any given height h, we have the weight of the total force on the winch is going to be the weight of everything, right, at any given height. And so that's going to be the weight of the platform in newtons and the weight of the cable. Well, the weight of the cable is dependent on h. If the platform is h meters up, then we have 93 minus h meters of cable. And every meter of cable weighs 151.77 newtons, so we're going to multiply. And that's going to give us the weight of the cable. All right? So we can start with, let's just start with the work for h. Can we do it? Can we write the function now? What would it be? Julie, what would the work function be? Yeah. Okay, so if a to h, yeah, we'll start with just the height. So we'll do 0 to h, okay? Because we said that, so what is it that we're talking about now? All this stuff is? The weight of the platform. 93 minus t, something else? Okay, and so then if we wanted to change the form of that to start from any starting height to any height above the ground, say x, then how would this be different? How would we change this? Yeah, it's just going to be now the integral from a to x, right? So it's just going to be an integral from a to x, and then we have the same rate as before. So the same rate of change of work. Okay, so, and then, of course, we know the beauty of having the function is not only can we get the work that the winch does to raise the platform all the way up, which might be the question, like how much work does it take in total to raise the platform all the way up? That would be, what would that be? W of 93, right? W of 93 then would be all the work to raise it up. But then this, having the function, then we know how much work it takes for any height, right? So how much work for 10, how much work is accomplished when the height is 10 meters, 20 meters, 33 meters, doesn't matter, right? So that's the advantage to having the function is we can get any amount of work anywhere along the way, including the total amount of work accomplished when it makes it to the top. Questions on this example? Yes, ma'am. But remember, what are the units here? So what's the units of mass? Remember? Kilograms. And then we have acceleration of gravity, which is meters per second. And that gives us what? Newtons, which is weight. So everything we had that were given was what given as what? Were we given mass? So we've got the weight of the cable is in newtons per meter, the weight of the platform in newtons. So do you see that just from the get-go in this problem, everything we had was already in weight, so that we don't need this. We don't need, so G would come in as if we were given things in kilograms. You see that? If we were given masses of things and we needed the weight, then we're going to multiply by G. But everything was just given to us as weights, as newtons. So then that wasn't, we didn't need that. Does that answer it? Other questions? Okay, so let's look at springs. A little time left. Let's look at springs. Questions on this example? Okay, so springs. So springs are subject to what's called Hooke's law. Hooke's law, it means that the force required to keep a spring displaced from rest is proportional to the amount of displacement. So in other words, that would be this here. So the force to keep a string stretched from its natural length is proportional, or K times its displacement. So no, X is not the length of this is key, X is not the length of the spring, but how much you've stretched it from its just at rest length, or natural length. So that's what we mean by displacement. So that is often a troubled point when you're doing these problems. You've got to make sure you know what X is. X is displacement from natural length, or unstretched length. It's not the whole length of the spring. Okay? It's the amount of change from the natural length. Okay, so make sure you got that. All right, so then K is the rate of change of force with respect to displacement. So if K is the rate of change of force with respect to displacement, how can we define this value K, going back to our broad meaning for rate of change? So K is the rate of change of force with respect to displacement. So this is one of our big themes at the beginning, and we've tried to keep it going. How could you explain the meaning of that value K then, if it's the rate of change of force with respect to displacement? Can I give you started? Given any. Tell the person next to you. If you know, say for a change of 0.015, every time you change 0.015, the force changes by 0.98 newtons. That means you could compute, having that information, you could compute, say for this spring, it's constant, right? So knowing that 0.98 is equal to K times 0.015. That means the constant for this spring is 65.33 Newton meters, and you could always say that the force required to hold it, X stretched by X meters, would be 65.33 times X. Okay, so what's the work? What's the work accomplished to stretch it X meters? What's the work accomplished to stretch it X meters? Go, write it down, quick. We got 2 minutes. Everyone write it down. What's the work required to stretch the spring X meters? Already asked Kellen. Already asked Julie. Already asked Rachel. Okay, this Hannah. Where's Hannah? Hannah, did you get it? What's the work then required to stretch the spring X meters? Or in other words, what's the accumulated work function for stretching the spring? Integral. Uh-huh. What you do? They like it. Because the force required to hold it then is going to be the same as what? The rate of change of work, right? That's what we said. The force is rate of change of work. So that force is our rate of change of work. So we got it.